All right, welcome back to another LeetCode medium problem, 2265. Count nodes equal to the average of subtree. I'm solving LeetCode problems a little bit interview style, where the focus is on communication, problem solving, and writing good code, more so than trying to come up with the shortest solution. But also to come up with a good runtime and space complexity analysis and trying to optimize the approach if we can. So the drill is that we first read through the problem description, check out the constraints. In a real interview, you would have to ask for all of the constraints and note them down. Then we're going to look at one example to understand the problem better, maybe get our first idea of how to solve the problem in code. Then by the end of looking at the example, we hopefully have an intuition of how we might be able to solve the problem. We will explain that, do a space and runtime complexity before we write any code, and then we will continue with the implementation of the solution. And and hopefully it works, and maybe we can iterate then to improve that solution. So let's get into it. Given the root of a binary tree, return the number of nodes where the value of the node is equal to the average of the values in its subtree. Note, the average of n elements is the sum of n elements divided by n, and rounded down to the nearest integer. A subtree of root is a tree consisting of root and all of its descendants. So, okay. So we might get 0 nodes, so root could be none. That's a good edge case we need to be careful with. And we don't care about how many... Wait, no, sorry, I made a mistake. So the value of the nodes between 0 and 1000, but the number of nodes itself is between 1 and 1000. The 1 means that root is never going to be none. But for our runtime analysis, we don't care that there's an upper bound, otherwise everything would be constant space and time, which is useless for our analysis. So, okay. So let's look at the example. Okay, so we have this tree, and we need to, let's count the average of, what is it called? The average of the values of its subtree. So 8 has a subtree of 0, 1, and 0 and 1. Let's look at this. For the node with the value 4, this one, the average of its subtree is 4 plus 8 plus 5 plus 0 plus 1 plus 6, which is 4. So that is actually counts for 1, right? For output 1. For the node with the value 5, the average of its subtree is 5 plus 6 divided by 2. Is 11 by 2 is 5. So this counts for another 1 in our output. For the node 0, the value of the subtree is also 0, so that counts as well. For the node 1, it's the same. So a leaf node is also a subtree, by definition. For 6, it's also 6. So all leaves are by default are accounting for 1, right? That's what I see here. So this is 3. This 4 and this 5. But for the 8, it's not true, because the average, 9 by 3, so the average is 3. Now for the rounding down, we could just do an integer division, right? So 5 plus 6 divided by 2 with integer, that is automatically going to be 5. Yeah, so we're going to use integer division for this to do the rounding down stuff. We don't need any other fancy math, I hope. Or fancy math functions that I don't know from the top of my head. Yes, so, well, how could we approach this? I think, well, we need to visit every node. We only have the root to start with, so we need to go down this tree, and maybe when we move upwards in the tree, we get the sum of the left and the right subtree, and then we do this check, right? We do this calculation, check it. And we update a result variable with +1 if this condition holds. So I think that's what we'll do. So we will do a depth first search approach. It's going to require O of n time because we need to visit every node once. And it's going to require O of h space, where h is the height of the tree, because we're going to use a recursive call. And the number of recursive calls is basically the space that we're going to need. Besides that, we only need constant space to store the actual result number. But yeah, so that'll be my approach. O of n time and O of h space and number of nodes in the tree, and h is height of the tree. Do we have any extra information about the tree? Just that it's a binary tree. It's not even a search tree or whatever. Doesn't matter. And h being the height of the tree. Right. Okay, cool. So, well, we're going to use a little recursive helper. The first search helper. And this is going to get a node. That is pretty much it. But it's going to return us an integer value, which is the sum of its subtree. Right? Okay, cool. If not a node, do we have to deal with the edge case? No. We know that we have at least one node. So yeah, so we're going to check whether we need to go into the left or right subtree. And one more thing that we need to do, we should also return how many nodes are actually in the subtree. Otherwise, we can't really compute, the divisor. We don't know what the divisor is unless we know how many different nodes there are. So this will return us a list of int. Let's say that. So, well, if we return also the number of nodes, then I guess we could actually do this check here. If node, we're going to do a bunch of computation. But if the node is null, if not a node, then what we will do is we will return 0, 0. So there's 0 here, but we're also having 0 nodes to consider. Now, left equals DFS helper, node.left. And we're going to do the same with the right. So we're collecting data here. Left sum and left nodes. So how many nodes we have? And, well, the subtree sum. And right and nodes. Maybe count is better. Count. And yeah, and we're returning the 0, 0 in the default case. So now what we need to do, we need to compute the total sum. So subtree sum is equal left sum plus right sum plus, of course, the node value, right? The value itself also belongs to that. And subtree count is the number of nodes in the subtree. So that'll be the left count plus the right count, but plus 1, because the node itself also counts to that. Now we do our little check. If the subtree sum divided by the subtree count is equal to node value, then we have to update our little result. And for that, we're going to use a variable that we define outside of our helper function, but we have access to that in here as well. And in the end, we're just going to return the result, but we have to call the DFS helper on the root node. That's pretty much it. And I see that we also have to perform this check at the root node. No, do we have to? No, we don't. We already, so if in the root node, in the helper, we will update the results if this condition holds true with the subtree sums, blah, blah, blah. So let me just do one more quick check. And that is our math here correct? So subtree sum includes the sum of all of the nodes. So 5 plus 6, so including the original node. And divided by 2, because we're getting back count 1 plus the count in here. And any leaf node or non-existent node will contribute 0 to the sum and 0 to the count, which is good. I'm fairly confident that this will work. I know that I'm kind of skipping looking for syntax errors, but that's because I'm a little bit tired. Okay, cannot access the local variable result. Okay, result. So there's a trick how you can do that. You just declare it as a non-local. If helper node dot left. So what is it doing here? Oh, we're not returning anything in here. We actually have to return the subtree sum and the subtree count as well. Otherwise, we're breaking the recursion on the way up, right? All right, so that passes the test cases. Let's submit it to see if it passes all of the LeetCode tests. And it does. Okay, nice. Yeah, let's have a quick look at some of the solutions. Let's check for something. That's a post-order traversal. That's basically what we're doing. You know, on the way out of the node, when we go back up, we do the calculation where we have the subtree information. Easy to understand. Why do people not add any runtime analysis in here? Typically you find them in the ones that use all the emojis that exist. O of n times space O of n. Well, we're doing better. We have O of h space. Because h is going to be smaller or equal than n, but yeah. All right, I think that's this problem. Yeah. Give it a shot, look away and try to implement it on your own. I think that's good practice.